Okay, in this video we're going to be thinking about if we have a graph with a set of vertices v and the size of v is equal to n, how many distinct graphs can we make, sort of by picking the edges? I know I did just say we start out with a graph. The real question is how many distinct graphs, I should put over here, how many distinct graphs G can we have that have n vertices? And distinct, so two graphs are distinct if one of them has a pair of vertices that are connected and the other one, so distinct graphs with the same, I should say, with the same vertices. So n vertices, right, with the same number of vertices, there we go. And so we'll say the vertex set is V, it's V1, V2, all the way through Vn, so it has n vertices. And the question is, think about it as, if we were given these n vertices, how many graphs could we make? I'll just do like a little sort of picture here to kind of give us the idea of what's going on with this. If we have these, 7 vertices, we could connect these two, and then these two, and then these two, and then maybe, I don't know, these ones. And that's one graph. That is a graph made with these vertices, and it has 1, 2, 3, 4. Well, that's not the laser tail here. 1, 2, 3, 4 vertices. Or we could have a graph that connects maybe these two, and these two, and these two, and these two, and that's another graph. And then in this graph, this one would be an isolated vertex. This would have no neighbors. And so the question is, how many ways can we do this? If you're given a set of n vertices, how many different graphs can you construct? And we're going to do a very nice little proof of this, which I like much more than the proofs you usually see in textbooks, which can be sort of cumbersome and long and annoying. This is one which is going to use, and this is probably why you haven't seen this in textbooks or something before if you're studying graph theory necessarily, especially if you're studying in computer science. It's going to use a fact about the number of functions between sets, the number of functions between two sets, which if you've taken set theory, this is sort of like a basic thing that you probably did really early on. And that's one of the things you can do with a little bit of extra math is come up with sort of cleaner, nicer proofs of these things, which are a lot shorter. So if we have two sets, if we have A and B, and for the moment we'll say that they are finite sets because you can generalize this if the sets are infinite, but for this we just need them to be finite because we have a finite number of vertices, and we can ask ourselves, what is the number of functions? What is the number of functions f going from A to B? How many functions go from A to B? And so in order to figure this out, we need to know what is the definition of, or what makes two functions distinct, just like two functions or two graphs are distinct if one of them joins a pair of vertices and the other one doesn't, right? They're the same graph if they join the exact same pairs of vertices. Two functions are the same we'll have A is equal to A1 all the way through AN. It has n elements, A1 all the way through AN. Maybe we'll do that in orange, the same color I did the set AN. And then the set B has m elements, B1, B2 all the way through BM. So it has m elements. They are both finite sets. And so two functions are going to be the same if they send the A's to exactly the same B's. So if f of AI is equal to f of B, or say g of AI for all, or we should use the logical notation upside down A for all 1 less than or equal to I less than or equal to n. So each of these functions, in order to be a function, it has to be, as we say, total. So it has to take each of these AIs and map them to some BI. That means it has to send everything somewhere, right? A is the domain of the function. So it has to send everything somewhere. And two functions are going to be the same if they send all of the elements of A to the same elements of B, right? So if F sends A1 to B2, and G sends A1 to B2, and the same thing for A2 and AN. Wherever F sends all of the AIs, g sends them as well, then they're the same function. So when we're trying to figure out how many functions there are, well, we start by saying, okay, how many choices are there for f of a1? How many elements of b1 could it send it to? Well, it could be b1, it could be b2, it could be b sub m. There are m, which is the size of b, and we're going to go with cardinality of b here. The size of b. There are b or cardinality of b choices for what we could map a1 to. Same thing for f of a2, right? There are cardinality of b choices for f of a2. And so the idea is that each set of choices that we make, so when we're defining a function from a to b, the way that we do that is we are taking each element of a and choosing which element of b it gets mapped to. So the number of different functions is the number of different ways to choose how we send these elements of a to elements of b. So the number of ways of choosing which element of b a1 gets sent to. Well, it could get sent to b1, b2, all the way through bm. And then when we were writing the function f as a set of ordered pairs, you may have seen this before. If not, do check out the video on this. We could say f of is equal to the set of ordered pairs a1, and then say if we decide to send it to b1, we would put b1 in there, and then we would put a2, and wherever we send it, we sent that to a2 gets sent to maybe like b5 or something like this. Any way of choosing these ordered pairs is a way of making a distinct function. If you change one of them, then you change the function, right? It will be different from the function. If I changed a1 to be sent to b3, then this function now would be different from the function that sends a1 to b1. So the idea is that the number of ways of choosing what we call values for so the value of a2 under the function f is the element of b that it sends that f sends a2 to, right? The number of ways of choosing the values for the elements of a is the number of functions from a to b. And we're seeing that for each one of these, there are size of b or cardinality of b, which is the number of elements in the set b. There's that many choices for which one to send each element to. So we have cardinality of b choices for each one of them. That means that if I look at how many ways to send, how many ways there are to choose the values of f for a1, there are cardinality of b choices for that, for a1. And then for a2, there are another cardinality of b choices. All the way through an, there are cardinality of b choices for how many elements of b I can send an to. And the number of functions, I'm going to multiply these, right? Because there are these cardinality of b choices for a1, and then for each of those cardinality of b choices for a1, I have another cardinality of b choices for a2. So you can imagine if just to make this a little bit concrete, say if a is the set 1, 2, 3, and b is the set 4, 5, and I'm thinking, how many functions are there between a and b? Well, I think about 1. I could send 1 to 4, or I could send 1 to 5. And then, and so these would be the sort of the beginning of two functions. And then for 1 and 4, now, so for this function, which sends 1 to 4, now I'm thinking about 2. Where could I send 2 to? I could send 2 to 4, or I could send 2 to 5. With this one, same thing. I could send 2 to 4, or I could send 2 to 5. And now how many total functions do I have? 4. There are 2, because there were 2 options for where to send 1, times 2 options for where to send 2. So there are 4 at this point. And then if you do that again with 3, you're going to get another 2 for these, and 2 for these, and 2 for these. And you're going to wind up with 2 cubed. 2 cubed, which is 8 functions from a to b. And this is the size of b, the cardinality of b to the power of the size of a, which is what we're finding out up here, is that is that because we had n elements of A, there were n elements of A, and we had m elements of B to choose from every time we wanted to define a function mapping each of these elements of A to an element of B, we wind up with cardinality of B, or size of B, to the power of the size of A. These are the number of functions from B from A to B. So the cardinality of the codomain B to the power of the cardinality of the domain, which is A. And if you're wondering, these functions don't have to be 1 to 1, right? You might have wondered, wait a second, how could we, here we could send 1 to 4, then we could send 2 to 4. That's absolutely permissible, right? We're not talking about the number of 1 to 1 functions. It's a very different computation if you're trying to figure out how many functions that are 1 to 1, so that they can't send 2 or more elements of A to a different element of B. That's not the case here. Here we have the possibility that all the elements of A could be sent to B1, right? It could map A1, A2, and everything all the way through AN to B1. Okay, so and with this in hand, let's go back to the problem. Back to our problem, which I'll just copy and bring down here instead of writing it again. How many vertices? And I'll just take, here we go, this. How many vertices, or how many graphs rather, can we make if we have n vertices? How many distinct graphs? And wow, and I copied the title. I'll just, I don't know, get rid of that. There we go. How many distinct graphs can we make with n vertices? Well, the insight to this is that each, and if we know this thing about the number of functions from a set to another set, we can notice that each graph G, which is the set V, and then some edges, which is the thing that we're determining, right? We have been given the number of vertices V, it's n, and we're trying to pick which edges we're going to. I meant to V here. There we go. V has size n. We're thinking of what are the number of ways of picking the edges. How many ways can we pick a set of edges to make a distinct graph? Well, each graph G we can think of as a function. We'll call it maybe phi from the set of vertices V to the set 0, 1. And why the set 0, 1? Well, the idea is that we're going to say phi of, and sorry, not from the set of vertices. Well, I almost made a big mistake. It's from V cross V. So from the set of ordered pairs. Actually, I should be even more precise about this. It should be from the set of VI, VJ, ordered pairs VI, VJ, such that VI and VJ are in V and I is not equal to J, because we're not thinking about connecting vertices to themselves. So it's not strictly V cross V. It's this subset of V cross V, the Cartesian product of V with itself, where we take the number of pairs of distinct elements of V. We're looking at the number of pairs of distinct elements of V, or the set of pairs of distinct elements of V, and we're mapping them to 0 and 1. And the idea is that V, or phi of V sub I, V sub J, is going to be 1 if VI and VJ are neighbors. So if they're connected to one another by an edge, that definitely does not say neighbors. GHOUB. Hold on. I swear I can spell neighbors. VI, VJ are NEIGHBOURS. I think there's a U. The idea is that they will be adjacent. We'll say adjacent. I can definitely spell adjacent. So if they are connected by an edge, if we connect VI to VJ by an edge, then phi of VI, VJ is equal to 1, and phi of VI, VJ of this ordered pair is equal to 0 if VI and VJ are not adjacent. So if they are not connected by an edge. So basically what we're saying is that this function, and so every function that assigns either 0 or 1 to every pair of distinct vertices is going to define a graph, right? If you're going to look at the pairs that it mapped to 1, and you're going to connect them and make an edge, and the ones that it mapped to 0, you will not connect and not make an edge. And every distinct function is going to give you a distinct graph, right? Because if some function, so phi1 of vi and vj is equal to 1, they're connected. Phi2, if it sends vi and vj to 0, then it doesn't connect them with a graph. They're not with an edge. They're not adjacent, and you get a different graph, right? So there is what we would call a one-to-one correspondence between the set of graphs with vertex set v and the set of functions from the set of ordered pairs of distinct vertices in V to the set 0, 1. Every graph, you just look at the pairs of vertices, and if they're connected, then you define phi of vi, vj to be 1. If they're not connected, or if they're not adjacent, I should stop saying connected, because connectedness is a property of graphs. If they're not adjacent to one another, they're not neighbors, then we define phi of vi, vj to be equal to 0. And so every graph will give you a function of phi from the set of ordered pairs of distinct vertices to 0, 1. And same way that every one of these functions will define a graph. And so once we've noticed this, right, once we've set this up and made this very important observation, well then what is the number of graphs? Number of graphs, of distinct graphs, is the same as the number of distinct functions from the set of ordered pairs of distinct vertices vi and vj in the vertex set V. So it's going to be, to 0, 1. So this is like the B from our example above, or from the little sort of proof that we did above. That's the set B. This is the set A. So we know that the cardinality, or the number of functions, distinct functions from the set A to the set B is going to be cardinality of B, the size of B, to the power of the size of A. In this case, it's going to be the size of the set 0, 1 to the size, to the power of the size of the set of all ordered pairs, vi, vj, such that I is not equal to j, vi, vj are in V. And I probably should have just assigned a letter to that, like S or something, so I wouldn't have to write it out again. But the question is, what is the size of this set? Right, so I know this one is 2, right? The size of the set 0, 1 is 2. This is 2 to the power of, well, what is the size of this set? How many pairs of distinct pairs of vertices? And so I think I've been saying ordered pairs. These are unordered. These are unordered. I just look at the round brackets and think ordered pair, but in this case they are unordered, because connecting vi to vj and connecting vj to vi is not the same, is exactly the same thing, which means that taking the set of ordered pairs, so taking the set which contains v1 and v2, but not v2 and v1, is not at all the same thing as taking the set which has v1 and v2 in it and v2 and v1 in it. So these are unordered pairs. But this is how we are going to, and I probably should have used set notation for this. I'm just going to keep going because I think people get the idea with this. But the idea is that if the fact that they're unordered is what allows us to quickly compute how many of them there are, how many unordered pairs of distinct elements vi and vj, which are elements of V, are there going to be? So how many ways can we choose two distinct elements of this set V, which has a size, its size is n, there's V. The size of V is equal to n. How many ways, so what is the number of ways to choose 2 out of n without, this is the key, without order, and I'm just going to throw in or replacement, because you can't choose the same vertex twice, that goes without saying. But maybe this jogs your memory about what mathematical tool we use to do this. What is the number of ways of taking 2 things out of n without order or replacement? Well, this is n choose 2. This is n choose 2, which I'm running out of space here, but we'll recall that n choose 2, or n choose k in general, is n factorial over k factorial times n minus k factorial. So n choose 2 is n factorial over 2 factorial times n minus 2 factorial. And you can cancel the factorials and wind up with n times n minus 1 over 2. It is n times n minus 1 over 2. because that n factorial is n times n minus 1 times n minus 2 all the way down to 1, and the n minus 2 factorial is n minus 2 times n minus 3 all the way down to 1. So it cancels with the n factorial, and you're just left with n times n minus 1 over 2. So the grand finale, the number of distinct graphs with n vertices is going to be 2 to the power of n times n minus 1 over 2. And so this is a very useful fundamental thing about graph theory, and a very nice example of how if we go a little bit, and this is why it's always nice to take other math courses outside of computer science or whatever you're working on, because if you this proof is a lot cleaner and simpler than a lot of the things that you'll find in a graph theory textbook where they're kind of dry and they do cases or something like this. Whereas I like to give what Paul Erdős would call the book proof of things, the sort of cleanest, nicest one, in my opinion at least. And we can very often get around having to do a bunch of horrible casework, which nobody likes, of course, although you have to do it in life. Sometimes life is just like that. You need to do cases. You shouldn't shy away from it by any means. But sometimes we can use slightly more advanced mathematical stuff. Like if we understand this thing, if we know and understand this thing about the number of functions from a set to another set, which is a very nice, important thing to know in and of itself, then we can just say, okay, well, as long as we recognize that each graph is a function from, if we think about fundamentally what is the activity we're doing when we make a graph, we're choosing pairs of vertices to either join with an edge or not join with an edge. Well, each of those choices of pairs of vertices from that set of vertices V, well, that defines a function from the set of unordered pairs. I almost said ordered pairs again. You just get so used to saying that phrase. The set of unordered pairs of vertices from V to the set 0, 1 with 0, and there's nothing special about 0, 1. It could have been 2 and 5. It could have been E and pi, but to a set with two elements where mapping a pair of vertices to one of the elements represents not joining them by a vertex, and mapping to the other one represents joining them by a vertex. As soon as you see that these sets are basically the same, right? There's a one-to-one correspondence between these things. Every graph gives you one of these functions, and every function gives you one of the graphs. And if the functions are different, the graphs will be different, etc. Once you realize that, then it's a very simple matter to apply the formula for the number of functions from one set to another, and get this really, really directly without a bunch of casework and stuff. So that's very nice.